let's see how it goes. But anyway, so welcome everyone to the first CHASC seminar of the season. And it's a talk that's being given by Matteo Guardiani of the help me out here, Matteo, your Max Planck Institute for
Astrophysics.
Astrophysics.
Exactly.
Okay, there are so many Max Plancks. So
I know.
at Munich, Garching. So,
Exactly.
Matteo, take it away.
Yeah. Hi, good afternoon, everyone. I'm happy to speak about. I was told that this seminar is quite informal, so I will keep it informal as well. So please, first of all, feel free to interrupt me if you have any question. And yeah, second of all, really, I try to make the slides as essential as possible and very light, since it's also evening here and lunchtime somewhere in the US. So I hope it's quite relaxing. But if there is any question or like you want to dive into the details, I'm happy to answer. Right.
One thing before you begin,
Yeah.
Matteo, I remembered what it was I was going to ask you. Could you send me your the slides as you know when you're done? So
Of course.
so we can
Of course,
put it
happy
up on
to do
our
that.
website. So,
Absolutely.
sure.
Will do. Right. So this is the work I've been carrying out for my PhD. I'm almost done. I'm a third year PhD student, fourth year now in Torsten Ensley's group, the information field theory group. And what we're doing is mainly imaging with a lot of side projects. And this is work that I mostly carried out with Vincent Eberle, Margaret Westerkamp, Philip Frank, who I heard has been at the CHASC recently, Julian Rustig, and of course Torsten, under Torsten's supervision. So what I want to what we usually look at in astrophysics is these beautiful data sets, which are somehow so we see, for example, in Rosita, supernova remnants and so on. And the issue with those sometimes for science is that these are not images. These are data sets which come with all their issues. And one can see, for example, point spread functions. One can see blending of different sources. And to draw scientific conclusions from these images, one would need to be able to disentangle the different sources and also try to get rid of all the instrumental effects. And this is precisely what we aim to do. I focus on a different data set, maybe visually less appealing, but still interesting. This was the data set that was collected during the first imaging, the first light of Rosita. And this is still in the, so this is in a field of view in the LMNC, quite kind of a small field of view. And well, small for Rosita. And yes, and what we aim to do is, of course, extract images from this data, but also separate different astrophysical components, point sources, and get rid of all these instrumental effects. For example, we can see the PSF quite clearly and how it morphs across the field of view. Right. And we do this using information field theory. For us today, information field theory is just a convenient tool that allows us, if we imagine to have some one-dimensional signal, for example, which is we can consider as ground truth, and then we draw some data, which maybe even has some masked region, allows us to reconstruct some posterior on this. And ideally, we would like to do this quite easily. So just by flicking or like spraying some magic paint on top of it. And one can see, for example, from this reconstruction that where the data was not informative, or where there was no data, the uncertainties are greater. And I mean, this is what one would expect from imaging in IFT, right? That somehow one could
Sorry,
use some software. Yeah, of course.
I missed, what is S?
S is the signal. Sorry, I don't think I said that, so
So
I
what is
didn't
the
miss any.
signal? I don't know. Can you be more specific? Yeah, we were
Yes,
looking at an
so
image of your, yeah.
this is just a synthetic example of like I draw some signal which could be anything right now as
So it's
far as
nothing to
we're
do with the example you just
concerned.
showed us. The VR.
Um, No, not yet.
Okay.
This is just like a very poor man's version of an introduction to IFT. So just as one has some signal with some correlation length, and one hopes to be able to reconstruct it from noisy data, maybe even incomplete data. Um, and the whole idea of information field theory is to be able to somehow quickly obtain a posterior on this. This is really, I try to keep it as basic as possible. So. I'm going through a one-dimensional example of what this is, and like this spray is, has this Ubik name, which is the title of my PhD project, which stands for Universal Bayesian Imaging Kit. And the idea is that we want to have software that does this, and we're developing the software here in Garching. So to do this, obviously, we cannot just spray some magic paint. What we have to do is we use Bayes' theorem, which I guess you're all familiar with, but I will remind you nonetheless. Bayes' theorem tells us that the posterior of some signal of interest constrained to the data is equal to the prior on this signal times a likelihood and normalized by the evidence. And I will go term by term to show you what this entails for astrophysical imaging. So first of all, the prior, what we're modeling right now is data. And in particular, we're trying to model X-ray data. And X-ray data is usually finite dimensional, hopefully. It is noisy and it contains non-invertible instrumental effects, which we want to get rid of. These effects are visible, for example, here, like PSF, which is varying across at different off-axis angles. And nonetheless, there's shot noise and all the nasty artifacts that we want to somehow get rid of. On the other side, what we ideally want to reconstruct are fields. These are infinite dimensional. So by this, I mean that they're continuous. So in principle, what could ask for the value of a field at any point in space. This is also a mathematical model, which doesn't necessarily have to resemble reality, but is often a nifty and handy way of describing a signal and of describing an astrophysical signal, for example. They vary in space, time, energy, or you name it. And they don't know about the instrument. This most importantly. So the brightness distribution of a galaxy or whatever we're looking at doesn't know about a Rosita that is going to observe it. So should it better not contain any visible, at least, instrumental artifact. So what does it
Can I
mean to
ask a
make a
quick
Yeah,
question?
of course.
So this is you're talking about S, the fields here or your S, right?
Exactly.
So is
Precisely.
it parameterized in some sense, or is it just on a point, a pixel wise or a point wise process? It's
Yeah, very good question. Yeah, we will get to this, but yes, it
okay.
is uh, it is a pixelated approach to this problem, the one that we're going to describe. Then this comes with its own issues that I will discuss. But yeah, so
Okay.
in some sense, it's non-parametric, yes, and hence the field
Okay.
idea. And it should be resolution independent in the sense that any question you can ask to the data, the answer should not depend on the resolution at which we bin, because in the end we always have to bin our fields on a computer, right? And to get some array out of it. But in principle, the approach should be resolution independent. Yeah.
Okay.
So this is kind of the goal. And this means that we have to make design a prior for these fields. And here I've just scrolled through prior samples of what does this mean. For example, for sky fluxes. A prior could look something like this. So I was scrolling through different draws from one of our priors, which has some diffuse emission, which doesn't have any particular meaning right now for us, and some point sources. How are these priors built? These are actually statistical priors on the sky. They're not necessarily physically motivated. And these are built through generative models. So what we do is we start from some latent representation of these fields, which is standard normal distributed. And then we apply some transformation to the to the distribution that we're interested in.
Do you
And
mean
in particular,
each coordinate, so each space in the continuum is normally distributed?
so we do Gaussian processes. So I will explain this better in the next slides, but yeah, the idea is that there is one standard normal distribution for each pixel, and then this gets convolved
I see. So
through a forward map.
we've left the infinite dimensional problem.
Yes, we have. Sorry. Yeah, that's a very good point. Yes, we have. So now we are on a computer, but a Gaussian process, I mean, there's a continuous representation for a Gaussian process that involves path integrals and whatnot, but in principle, one can connect the priors on the discrete grid to the underlying continuous representation. And we try even when we write our papers to always make this connection, because then we can really say that we're doing field theory, and this is resolution agnostic. So if you had highly resolved grids, you could in principle recycle the same priors, and that actually works in practice. So how we build correlated priors for these signals, for example, is by taking our white noise that you see here and convolving it with some kernel. And this is what I meant before as a Gaussian process. So for example, we start with the noise we've seen before, we convolve it with some convolution kernel, which basically has the underlying assumption that we a priori expect the signals to be homogeneous and isotropic, and then we get one sample of some diffuse emission. Of course, this is an art, and one has to know how to choose these correlation functions, these correlation kernels, and we do this in Fourier space. But now I'm digressing a bit, and I think Philip has already talked about this already here at CHASC, but I'm happy to go over this as well if you're interested.
Quick question though.
Yeah.
So by adopting N01 and this particular kernel, which I notice goes down to minus 0.5, so what exactly are you modeling the S? I mean, it's not plain brightness or intensity, which is positive definite.
Yeah, right now that's correct. Right now it's just some correlated signal. The idea is that these Gaussian excitations, together with the kernel shape, will be are parameters we want to optimize for, and in the end will adapt to whatever the data constrains them to. So this is just a generative model, so it's a quick model one can sample from. So one can draw very easily from a standard normal Gaussian, and we can also draw very easily from these kernels because these are again mapped to a standard Gaussian latent space. So one can draw very quickly from these kernels and these parameters, and then fit diffuse or point source emission to the data. And this is what
are you assuming that it's are you working in log space, log intensity space?
In most cases, yeah, for X-ray imaging, for sure, then we would take the exponential of this, for example. So there are some nonlinearities in the model, for sure.
Okay.
So to ensure, yeah, that's a very good point, to ensure positivity, for example, of the surface brightness. Or in principle, people have done even a lot more complicated models, so integrated densities or whatever, right? Magnetic fields in 3D. So, but for imaging, we try to keep it simple and just take an exponentiated, so a log normal Gaussian process and that is in most cases sufficient. But actually later I will show you a bit of a more complicated model for multi-frequency imaging.
Okay, thank you.
Was this clear?
Yeah, no, that's good.
Okay,
Thank you.
great. Yeah, so the prior we used up till so far for point sources was also similar. So we still start from a a Gaussian distributed latent space, and we transform it to something that is inverse gamma distributed instead of correlated, under the assumption that, so in each pixel, we basically draw from an inverse gamma. And this has been shown also by Fabrizia Guglielmetti, for example, that under certain assumptions is a good prior for point sources in the universe. Anyways, then our scribe prior samples.
Can you just say what that means?
Yeah.
So you sample in each pixel from an inverse gamma. Is that
That's
then
correct.
convolved with a kernel?
That's correct. Sorry, you mean the PSF kernel, or you mean?
In the previous slide, you had Gaussian noise, and you were convolving it with a kernel.
Yes. So
that's not the
here
PSF. That's about the blurring of the adding correlation to the independent Gaussian noise, right?
Exactly. Sorry. Yeah, maybe I wasn't clear on this. So this first example here is on how to draw prior samples for diffuse emission.
Yep.
So this has to be correlated, and therefore we correlated with a kernel. And then here I was just showing how one can draw a prior for point sources. So
and then I was asking if that was, you said an inverse gamma. So you said there's no kernel, it sounds like. So
there's no kernel. No.
Independently in each pixel, you draw an inverse gamma, which is a continuous distribution. So what does that represent in terms of point sources? The intensity?
So the brightness of the points, a point source in each pixel is given by an inverse gamma distribution.
So that means that there's a point source in every pixel.
That is very correct. Exactly. Sorry. Yes, I don't think I was clear enough on this. This is a crucial point. So in every pixel, we have a diffuse component. I was about to show this, but yes, we have a diffuse component and a point source component. And this is very costly and also very degenerate. And this is precisely, so you made a very good question, because this gives a lot of problems to the inference in the end, because the inference has to fight between diffuse and diffuse and correlated and uncorrelated emission. And depending on the data, this might be a very complicated problem. And so yes, so to go back to your question, basically, then a sky signal sample is formed by summing these two fields. So we have a inverse gamma distributed point source in every pixel, and we add a correlated diffuse emission component to it to get a sky sample.
Do you have some sort of a correlation in terms of spatial correlation scale for the point sources, or as it just?
Not necessarily. We have thought about this, but in the end, the models were getting more complicated, and yeah, we didn't really see an improvement in the fit. But of course, if you are imaging a field for which you have this knowledge and you want to put it in, this of course might improve your fit. So yeah, that is definitely something to look into.
Yeah, if you're looking at a globular cluster or something, you might want to concentrate your point sources in some location.
Definitely, you could draw them with some density function, and this actually. So for the inverse gamma, it doesn't really matter, because we always have a point source in every pixel. But for the model I will show you later, this is definitely something we've thought about. But yes, so yes, very good point. Yeah, and then one could even reconstruct the density of the globular cluster, for example, right? And yeah.
Also, I hate to throw this philosophical question at you, but this violates Olber's paradox, doesn't it?
Excuse me, this violates?
Olber's paradox of the universe being finite or not infinite. I mean, you can't have a point source at every pixel.
Oh yeah, yeah, no, of course, yeah. I mean, there's also absorption. There's many reasons why this prior is not a good prior, but it's a simple enough prior that one can sample from, and also like a priori, it's hard to say where a point source shouldn't be. And I will also show you how we then get rid of point sources where we don't believe them.
Sorry,
This also
can I just make a point?
Sure.
The idea of the inverse gamma is actually a transformation of the power law. So the idea that the stars in the universe are distributed according to a power law, this is a physical assumption. The problem is that a power law, you cannot normalize it. So at this point, you need to use an inverse gamma function. This is the origin of it. So it has a physical meaning, which then is translated into a statistical property.
Okay.
Power
Thank
law
you. That makes
also
sense.
can diverge at low values, though, which is what violates Olber's paradox.
Right. That makes sense. Yeah. Anyways, yeah. I mean, there's a lot of philosophy also already behind the inverse gamma, but I don't know if it's the right moment to go through this discussion. I don't know. Like we can, yeah.
No. Thank you. I mean, I was curious about
we can leave it to the end because it's something I've looked into and it's quite interesting also. But I think it's not so relevant for this particular talk. But yeah. Anyways, so once we get our sky signal samples, so our sky prior in the end, we need to build a likelihood, and with the likelihood, we like to describe all the instrumental effects that go from the signal to the data. So let's say that we observe this now synthetic sky realization that we made from our prior. So this is just a random sample from our prior. Then, for example, we have a Rosita that takes a look at it, and then we get some noisy data on Earth. And to be able to invert this process and from the data get to the signal, we need to be able to understand how a Rosita is morphing the original sky signal. And for that, we do some very gross approximation and we take what the calibrators at MPE have given us, so the data that is publicly available on how the Rosita PSF is shaped at different off-axis angles, and we approximate the response of our instrument with a PSF and an exposure. There's a lot of work, by the way, by Vincent Eberle, so also from the group, about representing efficiently these PSFs, because the PSF morphs with at different off-axis angles quite dramatically, and to be able to have to evaluate this efficiently is really an art. And yeah, we can also discuss more about that later. But for now, I will just say that we have a way to represent this efficiently. And then we also need the exposure. So in the end, if one puts all together, if we have some signal and we convolve it with our PSF response or approximated PSF response, we get already something that looks a bit more like the data. And then in our forward model, we also can include the exposure time. And then to draw synthetic data realizations, we can just consider this as a Poisson rate and draw Poisson realizations of this. So this would be in the end our likelihood. Yes, actually we used in the end also the cache version of this likelihood because we don't care about the normalization. But all in all, this is our forward data generating process, and this takes up 80% of our job, trying to make sure that the instrument model is accurate. In the end, we can also do some visual inspection and like make sure that at least visually things look similar. So our forward model is believable. So on the left I have some real data from Rosita, and on the right I have just the forward pass through our models, and we can see that at least visually there's quite some resemblance between the data and our machinery. So this is all good. We do also have the same for Chandra. I will quickly go through it just for fun. I mean, also there we are able to do the same thing and yeah, get synthetic data. And also there we get this resemblance with real Chandra data. Final step is what Philippa has already talked about extensively last time. So I will just very quickly remind you. So to then go back from our synthetic data to a ground truth signal, we can use variational inference, which is an effective way of doing inference in millions of dimensions, while still taking into account correlations and non-Gaussian posteriors. I don't know if there is any question on this. I'm happy to answer, but I think there was already quite an extensive talk with Philip. So in case you missed that, the video should still be online. And I think Philip is probably the expert to ask about GeoVI. But this using GeoVI, we can turn our simulated Rosita data, or like we can turn data into posterior samples. So we don't have access to the full million dimensional posterior, but we can get samples. And here you see in the region, yeah, I wanted to see, yeah, in the region in which the data, so in this bottom left region of the field of view, where the synthetic data was taken, there is quite some, there's little variance between the samples. Of course, some faint point sources change, but the main point sources are retrieved. And also there is some variation in the diffuse emission, but this is of course what we hope, in the sense that we are, since this noise, there's non-invertible instrumental effects. In the end, we hope that our samples kind of can give us a good representation of the uncertainty, and we calibrate them to these synthetic validations. So finally, the inference allows to turn our noisy data into some field reconstruction, and we can flicker back and forth between the ground truth and the reconstructed side to see how well we did. And in this synthetic example, I would say we did quite well. Yeah, here there's another comparison. And now the question is how to do point source detection on this, because of course,
so can you go back to that blink between the two? I'm trying to say which one is smoother. Is it that the ground truth is smoother than the?
I would say that for the diffuse emission, the posterior mean is definitely smoother, because it's very hard to narrow down at least on my screen, the higher frequency, let's say, higher spatial frequency correlation lengths. I mean, these are buried under the convolution with the PSF and the noise. But yeah.
I see. And I also see that in the posterior mean, sometimes there are several cases where there are additional clusters of sources.
Yeah, that is correct. So this is also the kind of making up for the positional uncertainty with that the convolution with the PS on the sources, right, on the point sources, that the convolution with the PSF brings, right? So once you convolve with the PSF, it's really hard to pin down the absolute location of the point source. So sometimes a point source will appear in a nearby pixel. Oh, oops.
The reason I'm asking is that we run into this problem with, for example, Lucy and Richardson, right, where you tend to pick up too many point sources. If you run it too long, it produces too many point sources. But is that an issue here? I mean, is a stopping point something you have to worry about?
Yeah, no, that's also a very good question. No, so there's no, in principle, the longer you could run these algorithms, the merrier, of course. There's a trade-off between what you get in the end and the compute time you can afford. I mean, for example, this example is very fast. It was run in 10 minutes on my laptop. But for bigger field of views or like higher resolution, then of course there is some trade-off between how much accuracy you gain by running the model longer. And so at some point you don't learn anything more from the data. But in principle, there's no stopping criterion in the Richard-Salusi sense that if you run it longer, then you get more sources, just because we have this prior, which acts as a regularization term. So there, yeah.
Okay. Thank you.
Yeah, of course. So in the end, let's turn at how we did or used to do point source detection with this model. What we used to do is, well, as you've seen, do a reconstruction, but since we had two components in our forward model, then of course we have the two components also in the posterior. And the problem is that for the point sources, one wouldn't really believe each pixel just because most of them will be under the noise. So what we did was have a look at these plots. Which show, for example, the ground truth the reconstructed intensity versus the ground truth intensity, and then decide a threshold. So, for example, this red line where the spread in fluxes was deemed acceptable, and then use this threshold to declare point source above this threshold. So anything below would just be cut out from our point source map, or at least deemed as unbelievable. Of course, the statistical effect would still be correct, because on average, this would contribute to the flux, but the singular point source, one would not believe below this intensity. And yes, this works, but it has many issues. So the main issue is that
sorry,
this is mainly
another question about the point source detection. Can you associate that red dashed line that you had with a p-value of some sort? I mean, is that equivalent? Does that become equivalent to what people usually would call 3 sigma detection or something?
Yeah, that is also correct, and we've done this in our latest paper. So you can ask the question of what is the probability of getting a fake, a false detection at this intensity, given the number of counts that you measure, for example, in the image. And yes, so you can set this threshold this way, and we have done this actually in our latest in our paper together with Margaret and Vincent, so Westerkamp and Vincent Eberle, on the imaging of the LMC. So in principle, yes, you can calibrate it this way, but you can also just choose an arbitrary by eye detection. In this example, I just literally picked a random cut. But yes, in a real astrophysical applications, we would justify this, of course, with some p-value, for instance.
And also, I mean, I suppose you can. I mean, I don't know if you tested this. Does this distribution is it stable for different levels of the diffuse emission versus the number of versus the brightness of the sources and things like that, right? I mean,
no.
Oh, okay. So, but
so there's a quick answer to this. This depends heavily on how well your instrument representation is, on how your instrument changes the signal, on, as you said, the interplay between diffuse and point source emission. If the diffuse emission is very peaky and has a very short range correlations, then it's even more degenerate with the point source flux, and it's even hard, and then the spread would be wider. So yes, but this is all to be expected, and it's all accounted for in the posterior uncertainty budget.
But if you can't do that, then how would you? So you can do this for a simulation because you know the true ground truth.
Yeah.
How would you do this for real data?
Yeah, so exactly. So for real data, we calibrate these thresholds on the simulation. So we do a simulation. We hope that we believe our
I see. So
simulation well
you
enough
make a simulation that is as close to the reality
as
and then
possible.
I see.
Exactly. And then, of course, the real data case will be worse, which has this approach has this drawback, but in
Yeah,
my mind,
yeah.
that's as good as you can do. If you know, you would.
Yeah, I think
You know the
Justina
ground.
has a question.
Yeah.
Yeah, thanks. In what you're describing here with the detection threshold, how do you distinguish between one very bright point source versus two medium bright point sources in the same pixel?
Right. You don't. You don't.
Okay.
Here we have one point source per pixel, and yeah, you don't have more than one point source per pixel. I'm not even
Okay,
sure
so
if
it's 0
one
or
could
1.
technically. Exactly.
Okay.
I'm not sure if one could even technically. So because in this case we're only looking at a single frequency image, so a single data, and I and in principle, yes, if you had more spectral information, then you could do what you suggest, and I will talk about this in a second. But with this model, no. You have at most one point source per pixel. I see that there's another question.
Axel, I think.
Yes, thank you. What about this horizontal bar at low fluxes? Is this the peak of the inverse gamma prior distribution? And why are not all sources on the peak?
This horizontal bar, you mean around 10 to minus 5?
Yes, exactly. Yeah, if you go to the lower left.
I don't know how to point with this, but yeah, I see what you mean. Sorry, your question if this is the peak of the inverse
Is
gamma.
it this one that you're talking about, Axel?
Yes, exactly.
Yes.
Yeah, this was one. And my question was whether this is the peak of the inverse gamma distribution.
Huh. To be fair, I didn't notice this. I thought this was a binning artifact, but no, actually, probably you're right. This might. I don't know. I would have to look into it. So this simulation I did more than a year ago, but it could be. Yeah, thank you for, yeah, I don't know. It probably. I wouldn't be surprised, yeah. But short answer is I don't know.
Yeah, thank you.
No, thank you. I would have to check. Yeah, that would make sense for sure. Yeah. So anyways, so this is how we used to do point source detection, and this comes with many problems, as I was mentioning before. The main problem is that point source detection is only prior driven in this, and I mean, this is not really a problem, but this is just a fact. Meaning that the only thing that constrains, so by changing your priors, you will get different results. And I mean, there's nothing one can really do about this in the sense that, I mean, the data only gives us the joint view of these two quantities. And by prior driven, I don't mean that the data doesn't carry information about spatial correlations. This is obviously how we break this, the degeneracy, right? So if we have correlated emission, we can safely assume that something's sticking out from this correlated emission as a point source. But yeah, this makes everything
Can I make
hard.
a quick comment about that? So yes, I believe it is prior driven, but for weak sources. For strong sources, it should be pretty stable, right? I mean, in principle, it's effectively setting your p-value high or low. It's a trade-off between false positives and false negatives.
Yeah, I guess what I want to say is that this is an issue more for the inference that for yeah, and yes, of course, for weak. So for strong sources, this separation is quite clear, but it is still prior driven in the sense that if I don't put a point source component in the pixel, I will never recover a point source.
I see it. Okay.
Because if I have, since we have the diffuse component emission everywhere, this is also free to explain point sources, right? And since we want to achieve this separation, things could in principle go wrong if we set up the priors very wrong in a way that the diffuse emission could eat up point source emission, even though you're absolutely right. If I have a very strong peak at a certain position, then this is most likely not some correlated emission.
Got it. Yeah, thank you.
This has another drawback, which is that this model has a point source in every pixel, and it's really hard to optimize, or it takes very long. Yes, I mean, and this third point is just summarizing the 2 points above. We want something quicker and something that doesn't necessarily assume that we have a point source in every pixel. I just wanted to show you how this works on real data. So here we imaged the supernova remnant 1006 with Chandra, and using this detection threshold still leads to quite nice results. So here I can blink, and one can see that one is still able to separate correlated and uncorrelated emission. Of course, there are some relics. There's a very visible point source in the center of the field of view that so of the supernova remnant that was not really captured. But we already know what went wrong there. So but there are more. Like so most of the point sources that were not image correct or separated correctly were at the edge of the field of view. And for this reconstruction, we didn't use Vincent's latest algorithm which has a spatially variant PSF. So then it makes sense that the convolution there didn't work perfectly. Yes. So all to say that this is not a terrible approach, but Chandra, as we know, has much better spatial resolution, and for Rosita, this same algorithm is giving a bit sensibly more problems, for instance, and we want to move to something else. So we would like to have automatic point source detection, and the idea to detect point sources automatically is to just use a different model. So we again continue with our synthetic example of mock Rosita data, and we try to fit it now only with the diffuse emission model. So we will only use our Gaussian process prior to fit the sky and completely neglect the fact that there are point sources in our model. This will create, so if we do so, this will create some posterior mean, which I'm showing here. And here you see that point sources are represented. This is kind of going in the direction of the question you asked before, Vinay. So in principle, the diffuse component is able to represent them, but you also see a lot of artifacts, because since we assume that the correlation kernel of this diffuse component is unique, is shared across the image, then we have to somehow explain point sources and diffuse emission with this kernel. And where data doesn't constrain it, this means that we will have a lot of small spatial scale artifacts. So you can see that the diffuse emission is not fluffy as it's supposed to be, but it's very pointy, and it has all these artifacts that come from the fact that one model component is trying to explain both point source and diffuse emission, and it cannot. But this also comes to our rescue in a way. Just to summarize, the problem with this fit is that we're using an assumption of spatial which assumes spatial correlations to fit something that is not spatially correlated, so the point sources. Moreover, this gets even worse when we do this in higher dimensions. So we will include the spectral direction, because we assume that somehow the point sources are also dependent from the Bragg and not independent, which is also wrong. And I mean, this is the same assumption we made before, but these point sources live on a grid, and the position of these point sources is constrained to the grid at which we bin the data, and this is also something we want to walk away from in India and idea of, or like in the spirit of what we discussed, that fields should be continuous. So now we go back again, and we want to, I want to remind you that which model we use to fit the data. So this model is basically a convolution between a standard normal distributed latent space and some kind of correlation kernel. And yes, so if we want to look at for locations in which the data was, so this model is somehow unhappy, so it's misspecified, then we can look into the latent space of this model. So if we imagine that our prior latent space looks like so, then the posterior on this latent space will not be standard normal distribution anymore, but it will actually have a different distribution. And from the location in which these excitations, we call them, these latent space excitations are mostly excited or high, we can read out that the model was unhappy because it had to go far away from the prior to explain the data. That's kind of the idea. And then if we compare this to the ground truth sky, if I blink, one can see that the locations at which the latent space excitations are high, we have actually higher point source flux, or like we have some point source. So then the idea is that we do a diffuse only fit. We find these locations we find these locations where the model is unhappy, and at these locations we introduce a new point source model, and only at these locations. And this makes the inference much easier and also much faster, and it doesn't make us carry around a point source in each pixel. And in principle, it could also allow for 2 point sources in one pixel, which was not allowed before. And this, the effect of this is that when we introduce the new point source model, we relax the excitations. This is some slide I had for a conference some time ago. And the excitations, after one introduces the point source model and reoptimizes, go back to their relaxed state, which is standard normal distributed, as we all know. So in the end, we also want to improve on the point source model we had before. And for this, I just want to go through a quick theory of what a statistical point source is. It's just some flux which is spatially uncorrelated, spectrally independent from the background, and doesn't live on a grid. And the way we do it is simply by interpolating some flux. So this is a unit point source at a certain location, is some flux interpolated at a specific location. So bilinearly even interpolated on the grid. And this makes it quite quick to evaluate, because this we always need in order to be able to invert the forward model. So obviously, if the point source center was at the center of the grid, then of course this would have unit flux. But now we also want to switch to multi-frequency data, because this carries a lot of information about different sources. So we see, for example, that if we take the data that we had at the beginning from the LMC, and in between 1 and 2 keV, then we see one sky. But of course, we have a lot more information, so why not choose, for example, 3 bands? And if we look at the sky at, for example, in the bands between 0.2 and 10 keV, 1 keV, and between 2 and 4.5, we see that certain astrophysical features, as we know, have different spectra. So, for example, the bubble, this Dorados 30 diffuse bubble at the northeast of the supernova remnant is very bright in the central frequency, but not as bright in other frequencies. And for example, if you look at, I cannot point, unfortunately, or I don't know how to, but if one look at certain point sources, one can see that they have very different spectra from the background. And this really is vital information for component separation, and we don't want to miss on this opportunity to use this. So we also need to make a multi-frequency forward model for the sky. This is a prior sample again of what this multi-frequency model will look like, and I will quickly guide you through the parameterization of such a model. So what we do is we take one of our diffuse, so we take a diffuse model that from before, so this Gaussian process model for a reference frequency. This is kind of setting the brightness distribution at reference frequency. It's basically telling us what is there at this reference frequency. And then the idea is that at higher frequencies, we can just assume this to be the brightness to be distributed as a power law. But since power law might not be enough for most sources, we also add another component, this delta component, that takes care of non-power law, so deviations from this power law, and this is a cube. And we make sure that all the this gets a bit involved, but we make sure that there is no degeneracy between this power law model and this delta, so this additional correction to the power law, by taking out any slope in this additional delta model cannot represent any power law. Let's say we take them out from the forward model.
Quick question about this.
Yeah.
So effectively, this is, I mean, including this factor of nu or nu naught to the delta. It is like having a very flexible form of multiplicative corrections to the other passbands.
Precisely.
So why do the power law form? I mean, why not just have a I0 times delta as your model?
Yeah, because that I mean, this is also a model that people have used. We wanted to put a bit more physical insight in the sense that for many astrophysical sources, we believe that the power law model is a good model, and fluxes actually vary on a logarithmic scale. But yes, absolutely, you could also and we have in the past modeled it with just a cube. Taking out these mapping out these degeneracies is, however, very essential. And if you have physical insight on a problem, it's often like astrophysicists always, because we're standing kind of in between. We're sometimes statisticians and sometimes astrophysicists, but astrophysicists oftentimes ask us to cook in a bit more physics in our models. And for most processes, power law is actually quite a good model to describe the spectral behavior. So we use it, but we know that it's not a perfect model, so therefore we add these deviations.
Okay. Thank you.
Yeah.
I mean, is it that the values that you get for the deltas are small compared to what you might get for alpha?
That is also baked in the prior. That is correct. Yes.
Okay.
I mean, you can set all these values. So the prior on these parameters you can set yourselves. In principle, one could also have high deviations, but at least in most cases, we prefer to have most of the spectral variation explained by the slope, and only deviations, for instance, lines, by explained by this delta term.
Okay, thank you.
I mean, lines would be very hard to model with this algorithm, but we're working on this as well. This is work in progress, actually. I mean, the model is available, but yes, it's also just the beginning of some work that will be carried out in the future. Anyways, if we have a look at these priors from these models, they're already quite convincing. So now we have we use the same model the same spectral model both for the point sources and the diffuse emission. And so the point sources also have this power law plus corrections in the spectral direction, but now they are unbound, not bound to a pixel. And as you can see, if I zoom in, because their flux value is interpolated onto a grid. Yes, so now we can go back to our original data and try to fit it. And if we fit, but we want to use this new latent space technique. And to do so, we take our model, and so just for the diffuse component, however, and fit it to the data. And if we look at the latent space excitation, we start seeing something interesting. So we start seeing that the peaks of this latent space excitations are actually at locations where we do see point sources. And what we also found out, though, is that we also can find extended sources because these also share a different correlation structure from the background. And therefore, this part has not been automatized, but we are working together with people from the Technical University of Munich, for instance. So Richard Fuchs has in place some neural network technique to build segmentation maps from these latent space maps, and then one can start a new reconstruction with additional components. But yeah, in my work, I only focus on point sources, but I just wanted to throw out the idea that one in principle can also detect extended sources and then reconstruct them. But what we have already done, so it's not the automatic detection of extended sources, but it's the model. And this we had to do, so I will go on a short digression why we developed them, because together with Julian Rustig, we have worked on strong lensing. So what we wanted to do then was reconstruct the brightness distribution of a source. In this case, you see some data from the SPT, so the South Pole Telescope galaxy 0418 minus 47. And the idea is that in strong lensing, for those of you who are not familiar, even though I assume most of you probably know, there is some background source galaxy that gets lensed. So the one that we were seeing before was at redshift 4.2, so quite high redshift. And the source galaxy light distributions get bent by some dark matter halo profile. And gets bent into some Einstein, what is called an Einstein ring, just by gravitational deflection. And but what we need to do in order to be able to reconstruct this source light distribution and also the dark matter or like the total mass, to be more precise, gravitational pull, is to have a prior for what a source originally could be. And here I will show again prior samples from our priors. These are quite flexible and can can explain different shapes of galaxies. And these are just also combinations of our Gaussian processes with some parametric, for example, a Sursic profile. And then we also had to do the same for the convergence. So for the projected gravitational potential. And yes, in the end, we were able to have some lens prior samples. So if we combine the lens light and the deflection on the observed signal, so on the lensed light plus the light from the lens galaxy. And this is work in progress that will actually come out quite soon. So we also have now a multi-frequency prior on the sources, just using the prior that you've seen before. And what we want to do is do multi-frequency fitting of lensing. But all to say, like, now we have a prior on extended sources, and we can, of course, if we get data on Earth, reconstruct the ground source signal, and here ground truth signal, and here we see the source reconstruction of the two companion galaxies at redshift 4.2 that we did with Julian. And yeah, so in principle, we have a prior also for extended sources, and we want to make use of this also in imaging. The only thing that is missing, going back to imaging, is automatic detection of these sources. One can still do it visually, but not automatically yet. So what we can do now is go back to our prior models and add some of these sources. some of these galaxies. And then what is always nice to me is to see that these are only statistical models for brightness distributions, but they kind of have the flexibility to represent something that almost looks like reality. So if one looks at these prior samples, one can see some resemblance with like images from JWST. But of course, these have no physics, or very little physics baked into them. Here I have a zoom in. And then the idea is that we can use such a model to fit the data. So if we go back to the data set we were considering, so this LMC data from Rosita, we can take the data, and these, unfortunately, I don't have time to really upload with the posteriors, so the most recent posteriors, but we can fit the data first of all, and then we can extract different components. But more importantly, since we have also extended components modeled, we can separate background and extended components, and then we can play all the different games, of course, of reconstructing the components independently and studying their fluxes and spectral behaviors alone. The nice thing is that we have a Bayesian method, so uncertainties come for free in the way we sample the posterior, so in this geometric variational inference. From this variational inference method. And if we skim through samples, we really see that this was not a converged reconstruction because the colors are completely different. So the spectral direction was not very well constrained, but we got it better. So this is the image from the preprint from my paper, which I actually got accepted last month. So here you see the final reconstruction of this data set, and you see how nicely we were able to separate these extended sources. So we have the Dorado 30C Doradus and the Tarantula Nebula from the background, all from this noisy data, and the point sources, of course, using this latent space field technique to identify the point sources. So yeah, if you like it and you wonder how to do this, now I will do a little bit of advertising. We are building up a pipeline and some code that is open source, which is called Jubic, which stands for JAX Ubic, because under the hood we use JAX, which is a machine learning framework from Google. For those who are not familiar, that helps with the automatic differentiation. That helps with the automatic differentiation and yeah, carrying around and also the multi device inference. So JAX is almost agnostic with respect to the backend. So one can run the accelerator, one can run on GPU, CPU, TPU, and the code in principle gives the same results. Jubic is built on JAX and NIFTY. So NIFTY is the software, numerical information field theory, the software that has GOVI, MGVI, so all the variational inference stuff, and the optimizer. And on top, Jubic offers likelihood models, so Gaussian likelihood, Poissonian likelihood, also these spatially variant and invariant PSF models, exposures. In the future, we want to add line models, and for example, pileup models, or whatever model you might like. For example, these point sources that distributed according to some global cluster density model. If Vina, you like to implement this. And so we have all the prior models, and we also have the prior models for the signal across different dimensions, so space, time, frequency. We're working on polarization and whatnot. And really the idea is that in the future, we will be able to take data from different instruments. For example, in the X-ray, we already have implemented Chandra and Rosita. We will work next year on XMM. There is not support on Jubic, but it has already been done within the group to image with gamma ray instruments, for example, the Fermi Large Area Telescope. We are working, for example, with people in Vienna to start building up the pipeline for ELT. VLT views also. In the infrared, we have JWST because we have implemented this for strong lensing. There have been people in the group that have worked on gravity. Again, ELT, big question mark. And the radio is soon gonna be available. It's on some branch, as most code is. It's not the main branch yet, but we want to integrate Resolve with Rubik. And the vision here is really to be able to do joint imaging, not only in a single wavelength, but really combining multiple wavelengths. And this should also help source detection, of course, and enable really to study the spectral behavior in a way that was unprecedented. And this is all our projects for the future. And I'm already at my outlook, so it wasn't that bad in the end. And the idea is that with exploiting latent space, we can use prior knowledge to solve these yield problems, because what we're trying to do is to constrain, in principle, infinite degrees of freedom with only finite number of data points. At even non-invertible detector effects can be using prior knowledge removed and taken care of. In principle, these methods have many other applications. So I was thinking about spectral lines, exoplanets. We have some application almost working for substructure detection and strong lensing. So watch out for that. A preprint is going to come out in the next month. And and also many more applications, joint imaging, interferometry, strong lensing, as I've said. So future work is, as I've said, fuse Rubik with Resolve. So this is a bit for those who know already the packages that exist from the information field theory group. Resolve is the package that is doing interferometric imaging. And this will also be rolled out probably at the beginning of next year. Enlarge our library of digital twins. This is where most of the time will be spent, because this really takes a lot of time to nail down the instruments well. And the instruments we're looking at mostly are Hubble, ALMA, ELT, but XMM. But yeah, we're happy to collaborate on any other instrument you might have in mind. Enlarge the library of calibration models, for example, PyLab, have more flexible PSF learning. There's people that try to learn the PSF, for example, with the stars in the field of view. This is something we're also thinking about doing. So there's a lot of future work. And also something very interesting that we were thinking about is to explore self and cross calibration. For instance, the idea here would be, for example, to take Chandra reconstruction, Chandra data to improve the calibration of a Rosetta, right? And because in principle you have this higher resolution in Chandra that can really help you nail down what the response of a Rosetta is, and then this will enable much higher resolution Rosetta imaging at lower cost. So that's or like even in regions where we wouldn't have Chandra observations. We also want to implement spectral line models and also enhance the support for multi-instrument data, because right now it is a bit painful to do it. We are, I think, in the next year especially, are going to work to make this a bit more user-friendly, that one can define a shared coordinate grid for observations at different wavelengths. With this, I finish with, again, a little bit more advertising. So Nifty, Jubik, and LensCharm, the softwares that enable all this work, are all available and open source. So I encourage you to play around with them and get in touch with us in case you have any question. And I thank you for your attention, and I'm open for discussion.
Thank you, Matteo.
Thank you.
It was a fascinating talk. We asked a lot of questions along the way. I don't know if people have any more. You're welcome to ask questions. There probably is not too many questions, as I said. I mean, we talked a lot. We asked a lot along the way. If you could send me your slides, I will put that up on our webpage, and we might have some follow-up questions. I personally, I personally have some thoughts about how this might be applied to solar data, which I don't know if you have thought about it. I mean, it might be a useful thing to try.
I have not. I know there's a lot of solar data, but
there is a lot of solar data, and it's extended emission with a lot of point sources, point-like sources. So it seems well designed for something like that. So
I'm very happy to discuss
curious
this.
to see how this would work out. Yeah.
Absolutely.
Yeah. Okay.
Do you have a question, actually?
Go ahead,
if there's time. Okay. For the multi-wavelength case where you were describing looking at different bands and X-ray data, then you had this, you had the model of the intensity at a particular band and then the almost perturbation in other bands. So if you combine, say, X-ray and gamma ray and optical data, then you have very different signal-to-noise ratios in the different bands. So then could you still use this approach, or would you have to do something entirely different? I guess for this, you have, with the power law, that's sort of presupposes that you're looking at similar bands.
That is a very good question. And yes, so for example, right now what we're doing is we're working on these SPT galaxies for lensing, and we're trying to image them using combinations of these models, but we cannot assume, so since the emissions even physically come from completely different processes, we cannot simply use this model naively. And what we do is share certain parts of these models, but in the spectral direction. For example, ALMA observations and JWC are already too far that we have to use two different spectral models. So we don't share the spectral model really, we share other parts of the model, but this is already good enough. But for example, in JWST, we have 13 bands right now we're looking at, and for those, this is a very good model. And in principle, we're planning to extend. I mean, one could have great body models, and we even have some implementation of these that are still non-parametrically learning the spectral direction. So that's a lot of work, and a lot of work that hasn't been completely finished yet. But yes, all of these are exciting avenues to be explored.
Sounds good. Thank you.
Thank you.
All right. So if there are no further questions, let us thank Matteo again. Very nice talk again, Matteo. So
thank you.
Hopefully you'll be able to come here again and talk to us in person next year sometime.
I hope so too. I'm sure it will happen next time.